Hello, I'm Reza Taimuri, lead developer of STE. In this tutorial, I'll show you how effortlessly you can set up a simple two-dimensional surface flow simulation in STGIS, and then walk through visualizing and analyzing the results. So without further delay, let's dive right in. Setting up a 2D simulation in STE software is very user-friendly and simple. We have included a tool for almost everything you might need, whether it's for downloading data or performing calculations. So the software will guide you through any challenges without any stress. In this tutorial, we are going to simulate and perform a simulation, very simple simulation for an area in United States. I simply go to the Tiles tab and activate Open Topo Map and go to the area I want to simulate in this tutorial. Okay, this is the area we want to simulate a 2D simulation, a water flow in this area. If you have a DEM ready for the simulation, you can simply add it to the software by right-clicking on the layer panel, going to the add layer and add raster item, or you can use add layer button here on the left, or maybe drag and dropping the file on the map or the layer panel, which make the software to open the raster here on the STGIS. In this case that we are performing the simulation, we don't have DEM ready for the area, which we need to download using the Open Topography DEM downloader, which is in the Terrain tab. I open the tool. What I have to do is to draw a area of interest polygon on the map of where I'm going to run the simulations. Simple as that. In the next step, I have to select my category. Since this area is inside the United States, I can use USGS DEM, which provide the data set USGS with 10 meter spatial accuracy. This tool in STGIS will automatically find the target CRS in UTM zone and reproject it automatically for your convenience. You might need an API key for downloading data from Open Topography DEM downloader, which if you have not any, you can use the link provided here to get one. You can save the file temporarily, and you can set an address for saving the file locally, and by clicking compute, the tool will start to download the DEM. As you can see, the DEM is downloaded and reprojected automatically and is ready for the simulation. For starting the simulation, we can come to the 2D tab, and here we have our tools for the 2D hydraulic simulations in STE software. In STE software, we have a setup wizard for setting up the 2D simulation very easily. This wizard will guide us through the necessary steps to configure our 2D hydraulic simulation. And as you know, for configuring this type of simulation and some essential items such as the terrain data, 2D area mesh, boundary condition, and simulation settings should be set accordingly. And after this setup, we can run the simulation. So I simply click on the next to go to the next step. In this step, we can set a simulation name, a simulation path to indicate where should the simulation files be stored, and we can set the equation set and the LIA theta and hyperparameters which is needed for the simulation. As you may already know, STE is capable of doing the simulation using the subgrid variability technique and classic meshes. If you want to know more about the subgrid variability and classic meshes, you can go to the 2D area mesh, which we will come in the few next steps, and by clicking F1, pressing F1 key on your keyboard, you can go to the documentation page on the STE website, which have descriptions and explanations about the differences of these two methods. Okay, we get back to the setup wizard and leave the subgrid variability enabled, which we want to use in this simulation to make it faster and more accurate. I simply select the DEM, which we just downloaded from Open Topography downloader tool. We could use the tool here. From here we could download and we can open our already downloaded DEM using this button. Okay, in this step we have to set our 2D domain and create our 2D area mesh. For creating a 2D area mesh for this area, I simply click on the button create 2D area mesh, and in this tool I want to create the 2D area mesh for my area of interest. For doing so, I activate the area of interest, and by clicking on draw on map, I simply draw a polygon on the map, which will determine where software is going to perform the 2D simulation. And then I have to define the spacings. This is equal to the spatial accuracy of my DEM, and I want to multiply it by 5, which will define my spacing in the 2D area mesh. Meshing is quite simple yet accurate in STE software, and just that easy you have done a 2D area setup and created a 2D area mesh. By clicking next, we can go to the next step. In this step, we can set and define some parameters for the subgrid variability technique, and there are some few options for advanced simulations such as subgrid computations, which allow us to make cells inside the domain finer, and we will create few video tutorials later for these options. In the next step, we shall set our data regions for the Manning roughness for the infiltration if we are simulating a rain-on grid, and bed material data regions if we are simulating a movable bed simulation and we want to simulate the erosion and depositions. So in this case, which we have no data regions for Manning roughness, we leave it blank, the data regions of Manning roughness, and we use the default value 0.06 for the whole 2D area. The software will use this value as Manning roughness for the whole area, and we will create tutorial videos on how creating data regions for the 2D simulation in STE software in the future. I click next to go to the next step. In the next step, we can determine and define our internal conditions. As you may already know, STE software lets you use internal conditions in the 2D simulation, which means you can have a cross section here and set a hydrograph for it to interflow from inside of your 2D domain. Or maybe you can use precipitation for applying rainfall on the 2D area and simulate rain on grid flow and simulation. In this simulation we have no internal conditions, so I leave this table blank and go to the next step. In the next step we have to set and determine our external conditions. External conditions can define the input and output flow to come inside to the 2D area and get outside of the 2D area. For this case we can use flow depths, water surface elevation, and flow discharge, and friction slope for a normal depth boundary condition type. Okay, since for this simulation we have no hydrograph entering the 2D area, I want to create a hydrograph based on this river morphology. For this case I come to the 1D tab and use cross-section analysis tool. In this tool I have to give it a cross-section to analyze the cross-section, so I use this button and I create a simple cross-section like this one. As you see, there is no geometry data, no bed elevation here, and simply I right click on the table and using get elevation values from DEM, using the item only this cross section, and selecting the DEM, high resolutional DEM, which we downloaded using the tool, we will get the bed elevation data set on this cross section and save it and get back to the cross section analysis tool. Here, by selecting the cross section we just created and loaded the data from DEM on it, we can analyze this cross section to see how much flow can enter from this cross section to our 2D area. I just want to have a full bank analysis with 100 number of rows in it, which here we can see a full bank and adequate flow for entering the 2D area can be 6 or 5 meter of flow depths. If I want to analyze further, I can click on analyze to see how flow is moving downstream from this cross section. As I mentioned, 5 meters of flow depths can give us 850 cubic meter per second as flow discharge. We can use this value to create our hydrograph for the boundary condition or external condition, better to say. For creating the hydrograph, I simply copied the value 850 cubic meter per second and I come to the tools tab. Using the hydrograph designer, I create a hydrograph using this template entered here. I set the duration of the hydrograph 500 minutes and the base value of 0 and peak value of 850 cubic meter per second. By simply clicking on generate hydrograph, my hydrograph for the 2D simulation will be generated. I simply copy the time first and come to the 2D simulation setup wizard. I already created a row, added a row here. I select flow discharge as input type and select the cross section we have created just here and click on the data to input the data. I have copied the time values in my clipboard and using the paste button here I can paste the time data, click OK to set the data, come back to the hydrograph designer, I click and I select the values, right click on it and click on copy to copy the data, come back to the data, the time series data, and paste it here on the column of flow discharge. Paste it here and I can see the hydrograph to be set correctly here. I click OK and now it's done. So we have set our hydrograph for input, but what about the output? The output of this simulation is here. But unlike most 2D flow simulation software such as HECRAS, STE is designed to let water exit the boundary by default unless a specific external condition is set by user to change that behavior. That means if you leave default friction slope a value higher than 0, the water will get out of the 2D domain if it reaches the boundary. Anywhere in the boundary, if water reaches, it will get out of the domain by the default friction slope which is set here. If you want to stop this, you can simply put 0 on the default friction slope and simply add a friction slope type of external condition and draw a line on where you want to let water get out of the 2D simulation, simply like it, and put a data here. We have a 500 time minutes for the input, and we can equally put a time 500 here for a friction slope and put 0.001 and 0.001 for friction slope to let the water get out of here. And one more notice I have to tell in this regard is that for flow discharge and in our analysis we used a value of 0.001 here, and we should put the value accordingly for the flow discharge. We almost forgot this. So for the flow discharge, to get input on the upstream, we have to set a friction slope. If you put 0 here, the software will calculate the value automatically using the DEM. So I set the values of the friction slope for the whole hydrograph 0.001 and set the values here. Okay, now this step is okay and we can proceed to the next step. The next step and the last step is timing and output setup, which the software, STE software, will automatically set the values based on your internal condition inputs and external condition inputs. As you see in this step, we have an external condition as flow discharge 500 minutes length, and the second external condition as friction slope to let the water get out of the 2D domain here, and the start time of the simulation is 0 and the end time is 500. So the software automatically set up the time frame here. We can simply select an output step for the outputs, and here we have 15 minutes and we'll leave it be. By clicking finish, the setup wizard will automatically configure the 2D simulator based on the information we provided. And in this tool, 2D simulator tool, we can review and change the settings if we want to, and have a look at it, change a few things if we want to. I should mention that STE automatically handles time step control for you, adjusting it based on the mesh and hydraulic conditions. It uses an adaptive time step that follows the CFL condition to keep your simulation stable right out of the box. This is a very robust system that will protect you from most instability issues. But if instability does occur, don't worry, just reduce the alpha coefficient and your simulation should run smoothly. Okay, we simply just click on the run simulation and let the simulation run, and as you see, simulation finished so fast, and we can post-process the result, and we could post-process the result in real time while the simulation is progressing. Here in the post-processor tool, we can click and activate the outputs we need, and if we want to see a specific output on the map, we can simply right click and select add to layers to see it on the map. In this case, I want to see the flow velocity, I right click and select add to layers. If you want to see the flow depths, I simply right click and select flow depths. So let's see flow depths on the map for this simulation. As you see, our created hydrograph simulated in this area using a constant Manning roughness value. We can make the simulation more accurate by giving it a spatial varied Manning roughness using the data regions, which we will discuss in the future tutorials. We can see the flow direction and flow passes using the particle tracing tool. I simply select time series for input raster and show velocity for making the particle tracing tool to show the velocity. So where the flow velocity is higher, the lines will move faster, and where it's slower and the velocity is lower, the lines will move slower. We can see the flow velocity on the map by simply activating it and see the flow velocity on the map. We can see the computation cells as polygons on the map for more analysis. We can see the outputs in profile lines just by coming to the Tools tab and use Plot Profile, drawing a profile on the map like it, and select DEM and select water surface elevation, and we can select flow velocity, but flow velocity might need a secondary y-axis for better visualization. And by using this scroll, I can see the changes of the variables through time. We can also see the values in time series, such as flow. But note that we have to create the flow discharge outputs here on the post-processor. I just click it to be created and post-processed. Once I have the data, flow discharge data, I can extract the time series data. I can draw a polyline where I want to have the flow hydrograph at that area and select the data on the flow discharge and plot no data values, change no data values to 0 and select and click on plot. I can see the flow discharge extracted from this area of flow and visualized here, and data is on the data table tab. I can export the data and use it. We can also visualize the results in 3D using the Tools tab, 3D visualization tool. I select the DEM, I give it more Z factor, and I select water surface elevation as time series. The water surface texture show the flow velocity, and click on start to see the results in 3-dimensional. As you see, the water is simulated and visualized in 3-dimensional. We can change the materials here, for example for the terrain, foam material and gradient, to see the bed elevation variations. And for water, I can use, since the water texture is flow velocity, I can use rainbow and full transparency to see where water has higher velocity. We can also download terrain texture for this area. For the area of interest, I use the polygon we drew initially, the same polygon we used to download the DEM, and we can use it to download Google Satellite. I simply click on download and let it download the tiles to use it as DEM texture. For doing so, we get back to 3D visualization, and here for DEM texture, we use the downloaded texture, Google Satellite texture, and click start. As you see, it is visualizing the results just like how it would be seen in the real life. We can change the materials of the water to be seen better here. Well, thank you for watching this video. I hope it gave you a clear and practical view of how easily 2-dimensional flood modeling can be set up and analyzed in STE, from downloading DEM data to running simulation and exploring results in both 2-dimensional and 3-dimensional. In this tutorial, we walked through the full workflow step by step and demonstrated how to post-process flow depth, velocity, and flow discharge, as well as how to extract time series and profile line data directly through the user interface. If you found this video helpful, please subscribe to our YouTube channel to stay up to date with upcoming tutorials and newly released features. You can also join our Telegram channel, where we regularly share updates, tips, and in-depth walkthroughs. Next video tutorials are on the way. Stay tuned.